Hello, everyone. Welcome to the Analog Electronic Technology course. In previous lessons, you've learned about the impact of the quiescent operating point on the common emitter basic amplifier circuit, and understood the concepts of cutoff distortion and saturation distortion. We must set a proper quiescent operating point for the amplifier circuit. However, in practice, factors such as power supply fluctuations, component aging, and environmental temperature changes can all affect the stability of the Q point and thus the circuit's performance. Among these, environmental temperature has the greatest impact on the operating point. Therefore, let's explore several ways to stabilize the quiescent operating point. First, from the component perspective, select components with better thermal stability. Second, from the environmental perspective, apply temperature control measures. Third, from the circuit perspective, introduce feedback. In this course, we focus more on circuit-level improvements to solve the problem of quiescent operating point instability. From our previous discussion, temperature changes lead to the following outcomes. As temperature rises, the reverse saturation current of the bipolar junction transistor increases, the current gain beta increases, and the base emitter junction voltage VBE decreases, ultimately causing the collector's static current ICQ to increase with temperature and shifting the Q point upward. To maintain a relatively stable ICQ, the circuit must automatically reduce the base current IBQ as the temperature increases. How can the circuit achieve this? Please carefully observe the following two circuits. Can you identify the structural differences between them? By comparison, the circuit on the right includes additional components: resistor RB2, resistor RE, and capacitor C. With these three components added to the basic common emitter amplifier circuit, we now have the circuit to be studied in this video: the voltage divider bias amplifier circuit. In this circuit, RB1 and RB2 are called upper and lower bias resistors. Their values must meet certain requirements, typically in the tens of kiloohms. In the DC path, due to the presence of RB1 and RB2, and under proper value conditions, the currents I1 and I2 through the resistive branches satisfy I1 equals I2 much greater than IBQ, allowing us to neglect IBQ. RB1 and RB2 effectively form a series connection, and the voltage at point B depends only on the power supply voltage and resistor values, independent of the bipolar junction transistor and temperature. Hence the name, voltage divider bias amplifier circuit. At this point, we obtain the expression for VB, which is temperature independent. Let's further explore how this circuit stabilizes the quiescent operating point.
When the temperature increases, how does ICQ change?
ICQ increases.
When ICQ increases, how does IEQ change?
IEQ increases.
As IEQ increases, how does VEQ change?
VEQ rises.
When VEQ increases, how does VBEQ change?
VBEQ decreases.
When VBEQ decreases, how does IBQ change?
IBQ decreases.
When IBQ increases, how does ICQ change?
ICQ decreases.
It is evident that the real reason the voltage divider bias amplifier circuit stabilizes the quiescent operating point is the emitter resistor, RE. Under static conditions, An increase in temperature causes IC to increase. Since the base voltage VV remains nearly constant, this current increase creates negative feedback through RE, forcing IC to decrease and maintaining a stable Q point. The larger RE is, the stronger the negative feedback effect, and the better the stability. So far, we have examined the functions of the lower bias resistor RB2 and the emitter resistor RE. Now a question: what is the function of the capacitor CE in the circuit? What happens if capacitor CE is removed? Construct a simulation circuit. Use a signal generator to produce a 1 kHz sine wave signal with a VTT of 5 mV. Input it into the circuit and use a dual trace oscilloscope to measure both input and output signals, recording the output waveform amplitude. Then disconnect CE and continue recording changes in the output waveform amplitude. Compare the waveform amplitudes before and after. From the simulation experiment, we can clearly observe that after removing capacitor CE, the output signal amplitude drops sharply. CE is connected in parallel across RE, providing a path for AC signals. In the AC path, it effectively shorts RE, preventing the amplifier gain from decreasing due to RE. The voltage divider bias amplifier circuit was widely used in cassette recorders, audio systems, color TVs, and other appliances during the 1970s and 1980s due to its ability to stabilize the quiescent operating point. With the development and maturity of integrated circuit technology, such discrete circuits have largely been replaced by integrated blocks, but the fundamental principle of stabilizing the quiescent operating point remains reflected in modern circuits. At this point, can you also feel the rapid development of the electronics industry? Therefore, only by building a solid foundation and accumulating knowledge can we keep pace with the times. Finally, let's summarize the key points of this video. 1. Structural features of the voltage divider bias circuit. Addition of lower bias resistor RB2, emitter resistor RE, and bypass capacitor CE. 2. Performance features of the voltage divider bias circuit. Stabilization of the quiescent operating point through negative feedback provided by the emitter resistor RE. 3. Function of emitter bypass capacitor CE. Provides a path for AC signals, preventing the amplifier gain from decreasing due to RE. Alright, that concludes this lesson. Thank you, goodbye.